So, we had stopped at this equation in my last lecture, which gives the wave value, or I will not say intensity, I have not yet taken the intensity, at the point z where we are making all the measurements. Okay. So, of the second harmonic generated wave, this is the second harmonic generated wave, and this is the final final electric field equation of that wave at the point z. So, again, as I say, it is a secondary electromagnetic wave. The wave has a double frequency 2 omega and has a varying amplitude. Okay, the part to be concentrated on is the varying amplitude. So, I will just forget about this for the moment and look at this varying amplitude. Okay, A 2 omega is A sine of omega z delta n by c. So, your delta n comes here and delta n comes here also. Generally, for intensity we take E star E or E square. Okay. So, I will take the square because we are interested mainly in the intensity of the second harmonic generation. So, then this amplitude also will become square. So, I have just put it square there, squared it. And where does this term z square come from? I have just put a term z here, so that it looks like the argument of the sign, the denominator looks exactly like the argument of the sign. So, I have divided by z, so I have to multiply by z here, and that is how it becomes a z square term. Okay. So, here I am. This is after taking the square, we are looking at the intensity. So, let us see what this sine term looks like, sine square term looks like. You know, sine square term is an undulating, it is an undulating wave like this, and this axis is obviously the z axis, and this axis is the amplitude axis. Now, when does sine become maximum, sine curve? At pi by 2, you will get a trough at pi for a sine curve, you will get a maximum again at 3 pi by 2. Okay. So, here this argument should be pi by 2 in order to get the maximum amplitude. So, here I put it omega delta z, in place of z I have put it as delta z. So, it gives you the length that it travels. So, omega delta z delta n by c is equal to pi by 2. Rearrange the terms and you get delta z is equal to lambda upon 4 delta n. I call it LC. I call this distance delta z as LC. LC is called the coherence length. One can generate the double frequency by a high power laser beam through a plate whose thickness is equal to the coherence length. Okay. So, you can see here I am getting a maximum intensity at this pi by 2, and this small length here, this much, is LC. Again, after another LC, a travel of that distance of LC, okay, the second harmonic intensity goes down. Again, a travel of another LC, the second harmonic goes up. So, what is happening? This is not what I am looking for, but this is what is happening. So, if I have a very high power laser beam and I pass it through a plate, any plate which is transparent to the primary frequency, and this is LC, the thickness is LC. So, I have a very high power laser beam here, high intense laser beam, the primary beam, and you get a second harmonic here output. It has been seen experimentally, you do get one second harmonic there. Okay. But the point is, however high the intensity may be of, of your primary beam of frequency omega, the second harmonic that is generated is always very feeble. Now, what would I intuitively feel? That suppose I had a thickness which is more than this LC, perhaps I could get a higher intense second harmonic beam. But no, it does not happen that way. If you increase the length to twice of LC, increase the plate thickness to twice of LC, you will come to this point. You will come to this point. That means you are not getting any second harmonic generation at all. Again you increase to go to 3 LC, you will definitely see a second harmonic generated, and it has been seen experimentally. So, the second harmonic that is generated is quite feeble. Now, what can be done about it? So, what is really happening? Now, I am increasing the length of my plate, increasing the thickness of my plate, and yet my second harmonic is not going up. And I can increase the intensity of the primary beam, still nothing much will happen. So, what is exactly happening is, when the primary beam and the secondary second harmonic generated beam are traveling in the same direction, they are transferring energy from one into the other. So, as it is going by, the primary beam, the omega beam, is transferring some of its energy into the second harmonic, and you are getting a high peak, and then the second harmonic is transferring it back to the primary beam. So, this is not what I am looking for. Okay. So, but just have a, to increase the radiation intensity, it is necessary to increase the coherence length by decreasing delta n. In the limit of delta n tending to 0, the coherence length LC tends to infinity. Okay. So, if I go back here, you look here, LC will be infinite if delta n tends to 0. Okay. So, can you have a plate which has a thickness infinity? That is also an impossibility. Or can you get delta n to be 0 in that same material through which the radiation is passing? The value of delta n depends on the properties of the nonlinear medium and cannot be decreased arbitrarily. So, you cannot just get delta n equal to 0 in a medium, you can't decrease it. The refractive index is fixed for that medium, and the refractive index is fixed for a certain frequency, omega. So, what can be done? So, here again it shows that when delta n tends to 0, you can perhaps get delta n is equal to 0, you can perhaps get a higher intense beam. Okay. We have seen it earlier also in the previous slides that delta n equal to 0 is necessary. Now, what can be done about it? Have a look at this undulating amplitude of the intensity. Look at this term. So, this looks like a term like this, sine square x upon x square, this part looks like this. When delta n tends to 0 or when x tends to 0, this limit becomes 1. So, when delta n becomes close to 0, this limit is 1. It is no longer a trough there at 0. You get a peak there. Okay. You get a peak, and in this undulating part. So, and this peak a 2 omega is equal to a z square. This is really lucky, a z square. So, that means you can increase the length of travel of your primary wave within the transparent material. You can keep on increasing the length through which this primary wave is traveling, and you will get higher and higher second harmonic generation, and it goes by z square. Okay. So, as you increase the length, you are getting a higher intensity generation for the second harmonic, and that is what we want. So, phase matching is important, and once you have got this phase matching, that means once delta n is equal to 0, which is called the phase matching, you can easily increase the thickness of your crystal, okay, through which your primary beam is passing. You can increase the thickness, and you will be rewarded with a higher intense second harmonic generation. The frequency doubling effect is the pumping of energy from one wave to another with a double frequency. The phase matching condition must be satisfied in order to ensure that such an energy pumping is in one direction for a long time, so that these two waves are not transferring its energy from one to the other, but only the primary wave is able to transfer its energy to the second harmonic wave, okay, and that is what we want. But the question is how? How can we get delta n to be 0? How can we get delta n to be 0? We cannot arbitrarily decrease the properties, decrease the refractive index in a medium. We can't do that, but still we have to look for method of getting delta n equal to 0. Delta n equal to 0 means n omega should be equal to n 2 omega. It is possible. It is possible in birefringence, in anisotropic medium, which are specifically birefringent in nature. Delta n equal to 0 is possible there. So, you have heard about crystals like calcite and quartz, through which double refraction in crystals take place. Example is calcite and quartz. Actually, the first time when double frequency generation was demonstrated was in 1961 by a ruby laser in a KDP crystal. It gave a second harmonic of the ruby laser. And from then on, of course, there were many other crystals and many other wavelengths which have been frequency doubled. So, they have all been frequency doubled in birefringent crystals. Okay. So, I will just take the example of say calcite and quartz. You may have even seen quartz. It may be a very rough crystal. Its quartz is very easily available in many places. So, I don't know if you've done such an experiment before. Suppose I have a spot here. Okay. You place a quartz crystal on top of this. You have a paper. You just put a spot there. You put a quartz crystal there, and when you look through that quartz crystal, you will actually see two spots. You have drawn only one spot, you look through the quartz crystal and you see two spots. This is double refraction. Okay. So, what happens here is the light is split into two different rays. One is called the O ray and one is called the E ray. One is called the ordinary ray and one is called the extraordinary ray. So, in my subsequent lectures, I will be dealing with the ordinary ray and the extraordinary ray, okay, and how that will help me to achieve delta n equal to 0. Okay. So, before I go into that, let me give you some here I have just tabulated some examples of different types of lasers and frequency doubling in that. So, quite often it is called frequency doubling. So, in case of say ruby laser, it is 694.3 nanometer and the input frequency is 4.32 into 10 to the power 14 hertz. Okay, this is in terms of frequency, and it can be frequency doubled in a KDP crystal or a BBO crystal, beta barium borate crystal, and the frequency doubles into this frequency. Okay. So, frequency doubling means half the wavelength. Okay. So, half the wavelength of 694 is generated and that is 347.15 nanometer. So, this comes in the ultraviolet region. So, from the red region, from a red wavelength, you have gone very close to the ultraviolet wavelength. Though it is called frequency doubling, very often we refer to the wavelength which is halved. You say the ruby laser is frequency doubled, but then you will be giving this factor 347.15 nanometer. Okay. It is the wavelength which is halved. When you refer to the ND YAG which is in the near infrared 1064 nanometer, it frequency doubles or wavelength half into 532 nanometer. So, it comes into the green region from the near infrared. Carbon dioxide laser at 1064 micrometer, it can be frequency doubled in ZGP, gallium selenide and such crystals, and the wavelength is half to 5.32, which is also in the near infrared. This is sort of far infrared and this comes into the near infrared. Titanium sapphire laser in 800 nanometer, it can be frequency doubled in BBO, KDP and LBO. So, KDP seems to be a very popular crystal in which frequency doubling takes place. So, we will look into the KDP crystal as the best example, and okay, so the titanium sapphire frequency doubles to 400 nanometer, which is again deep blue close to the ultraviolet. Okay. So, these are some of the examples. So, so let's dive into this completely, but before I do that, let me just remind you that the E ray and the O ray, ordinary ray, it is called ordinary because it follows the usual laws of light. It follows Snell's law. That means n1 sin theta 1 is equal to n2 sin theta 2. But the extraordinary ray or the E ray, it is really extraordinary. It just does not follow this Snell's law. It has its own rules of its own. Okay. So, we will see how that happens. Just keep in mind the E ray and the O ray. Okay. Now, let me just give you a little bit, you recollect what is Snell's law. I have a slab here, a denser slab, and this is the air. The beam ray is coming in here and it gets refracted and it gets reflected. Okay. So, the refracted beam follows this principle. Okay. N1 is C by V1, N2 is C by V2. N1 and N2 are the refractive indices of these two medium, air and this bit of glass. So, this you know this very well, Snell's law, but what you may not know or may not have thought about is that the refracted ray gets polarized, partially polarized, and the reflected ray is almost completely polarized. Okay. So, what I show by this, what is the input beam? Input beam is an unpolarized light. Okay. And I show that unpolarization by this green. This is the electric field is vibrating in this direction. By this green arrow, I show this the polarization in one direction, and the circles here, blue circles, is the polarization in the perpendicular direction. So, it is perpendicular to the screen. Okay. And here similarly. So, when I show it on top of this, it means it is unpolarized. Here I have shown the green arrow and the circle here separated because they are partially polarized. Okay. And this is again, the polarization is perpendicular to this screen. The reflected beam is almost always completely polarized. Okay. So, I will come across this E ray and the O ray is also they are also polarized beams, and they have a polarization which is perpendicular to each other. So, before I go further, I can give you a little bit of idea of what polarization is. And it is not exactly, do not confuse it with the polarization that I have been talking about till now, P to omega. It is slightly different from that. Okay. The P, the polarization which is induced, has something to do with the medium, while here the polarization is the polarization of the light itself, of the beam of light, of the electromagnetic wave. Okay. So, let me just give you an idea of the polarization. So, the polarized and the unpolarized light differ in how the electric field and the magnetic field, which make up the light waves, are oriented as they travel. Okay. So, let me show it to you here. Suppose I have, this is, okay, the light is traveling along this direction. Okay, polarized light would mean one polarization. Okay. So, the electric field is vibrating on the plane of this paper. Okay. On this paper, just imagine that the electric field of this beam of light is vibrating in the plane of this page. Okay. Now, the electric field can also vibrate something like this, if I am able to draw it. So, this is the vibration of the electric field, which is perpendicular to this plane of this paper. Okay. So, both these separately are called plane polarized light. Okay. Now, you can have another type of polarization where the beam, the electric field, the vibrations of the electric field, which is shown here, can have a kind of a structure like this. I may not be able to show it to you exactly on this. So, the electric field is like this, like this, like this, slightly crooked here. Okay. So, this polarization is different from these two. it is not always on the same plane, it is slightly deviating from this plane and the one perpendicular to it. So, what I can say is, if I were to look at it from this direction, then this would be tracing a circle. This electric field point would be tracing a circle if I am looking at it from here. And a generalized case is it could be tracing an ellipse. So, the first one is in only in one plane, this is also in another only in one plane, but perpendicular to this. These are plane polarized light. Plane polarized light, while these are circular or elliptically polarized light. Okay. So, it is this is a concept, we will be dealing mainly with the plane polarized light now. This is just for your information, but for the moment we are not dealing with elliptically or circularly polarized light. Okay. So, see, it is a concept which you have to know, which you have to there is no measure for it, but you can measure the consequence of that. You have a plane polarized light, and if you put a polarizer and an analyzer, your intensity will grow or become less or become more depending on the orientation of the polarizer. So, that is the way of measuring or detecting a plane polarized light. You got a hint of that when I spoke about the Pockels cell which acts as a shutter in mode locking. Okay. So, the plane polarized light is a concept as I have given here, and you can measure its consequences. Okay. So, we will go further beyond this in my next lecture.